previous class we spoke about arithmetic series, but in this class we're going to be looking at geometric series. And in simple definition, geometric series can be defined as the sum of the terms of a geometric sequence. So for instance, we said that assuming we have u1, u2, u3, u4, u5, even all the way down to say un to be the terms of a geometric sequence, then u1 plus u2 plus u3 plus u4 plus u5 plus all the way down to un would have been the geometric series. Adding up the terms of a geometric sequence give rise to a geometric series. Albeit, just like graph in AP, there are formulas that we use in solving, in adding up terms of the geometric sequence. But there are constraints placed on this formula based on the common ratio, based on the shape or the value of the common ratio. So look at the formula. Basically, three of them. We have Sn equals to A in brackets r raised to the power n minus 1 all over r minus 1. This formula is used when our common ratio is greater than 1. Meanwhile, the second of it that looks like it is this, A open bracket, I'm going to change the position, 1 minus r raised to the power n, change the position, 1 minus r. This is used when my common ratio is what? Less than 1. So that I will not need to be creating extra videos, I'll just talk about the sum to infinity in the same slide. So the sum to infinity is defined as S infinity equals A all over 1 minus r. This is applicable when our common ratio is less than 1. Albeit, the sum to infinity of a GP when the common ratio is greater than 1 does not exist. It does not exist. That being said, it means that what determines which of the formulas I'm going to use is the nature of my common ratio. You understand? And do not forget that the sum to infinity of a GP of an AP does not exist. There's something called sum to infinity of an AP. That does not exist at all. That will be noted. So that we can buttress our points more, I'm going to be writing 1 or 2 examples. I'll go look at them, and that will be okay for us to solidify our point. So, for example, look at the example now. Find the sum to the nth term of the following geometric progression. X. Solve for the sum to infinity, sum to infinity where applicable. So look at that's an example where applicable has to solve for that. See number 1. Let's say test 6 very simple example. Now note that it's very simple does not mean it's not applicable. It doesn't have to be difficult as it is. So this is a very, very simplified example that you can easily use in solving your work out. So let's see. I'm going to give one more example. That's going to be your own classwork to see how far you're doing. So look at, we have, let's say we have 20, let me say I have 9, I have 3, I have 1, I have yes, I have 1, and it goes on and on. This is also my geometric progression. Number 3, then we have 1 over 8, 1 over 4, 1 over 2, and it goes on and on. So, how do I solve these questions? That is the question that we have on ground. How do I fix this? Kindly keep these 3 formulas. I'm going to write on the board except the question so that we can solve. But do not forget this. If you have to write it down, I'm going to make reference to them as we go on in the class. You're once again welcome. So let's fix number 1 example. Look at the 1 example where we have 2, 4, 8, 16, and so on. Now, first thing first, what is my common ratio? U2 and U1. You should understand the drill by now from our past videos. 8 over 4, 16 over 8. So 2 here 1, 2 here 2, 4 here 1, 4 here 2, 8 here 1, 8 here 2. So my common ratio is simply equals to what? 2. 2, 2, 2. So simply 2. And what's my first term? My first term is 4. Now having 2, which of the formula is applicable? Is it the one I wrote first, SL equals A in brackets R square N minus 1 over R minus 1, or the second, which of those is applicable? Definitely the first one, because our common ratio is greater than 1. Our common ratio is 2 and greater than 1. Any other formula is not applicable. So that being said, I've now said we call that what? SL equals A open brackets R square N minus 1 over R minus 1. And we're using this because R is greater than 1. That is 2 is greater than 1. So S what? S, okay, find the sum to the, don't say ends, S say 8 star. So S8 now is now equals to, what is my first term? 2. What is my common? Oh, common, my first term is 2. So what is my common ratio? 2. What is my n? My n is 8 minus 1, all over what? All over 2 minus 1. So I can easily divide this and say S8 equals 2 times 2 raised to power 8 should be 256. 256 minus 1, all over 2 minus 1 is 1. So what do I have? I have 2 times 255, which will give me 510 eventually. So this is the sum to the 8 star of my progression. And I'm using this formula because my common ratio is 1. So let's try the number 2 part of the question. I'm going to be wrapping up this book. But before then, don't forget, we are asked to solve for the sum to infinity applicable. Is sum to infinity applicable here? No. Because sum to infinity is only applicable when our common ratio is less than 1. But here, our common ratio is greater than 1, so we cannot solve for sum to infinity. Is that clear? So let's try number 2 question. Okay, for number 2 question, what do we have? Number 2, we have 9, 3, 1, and it goes on. We have been told that it's a GP, so we need to stress ourselves. So, what are common ratio? Simply 3 over 9, u over u1, then 1 over 3, 3 over 1, 3 over 3. Our common ratio is 1 over 3. The question is, which of the formula is applicable to solve for the sum to the nth of the GP? Is it the first one or the second one? Definitely the second one. Because 1 over 3 is not greater than 1. Instead, it is less than 1. So we are going to be using the formula, say, Sn equals A open bracket 1 minus R square N all over 1 minus R. That's what we're going to be using. So that being said, that's my A. My A is 9. A is 9 open bracket 1 minus 1 over 3 all to the power of 8 all over 1 minus 1 over 3. Do you understand? So that being said, we can easily say that commonly, we just want to simplify now, 9, and I have my LCM to be 3 raised to power 8. When you expand it, how many, because it's 1 over 1, how many 1 can you say 3 raised to power 8? 3 raised to power 8 times 1, 3 raised to power 8 minus 3 raised to power 8 in 3 raised to power 8 is 1, 1 times 1 is 1. Then all over this minus this is 2 over 3. Do you understand? So that being said, I have 9 times 3 over 2, open bracket, 3 raised to power 8 minus 1, all over 3 raised to power what? 8. You get? So this will give me what? 27 over 2 multiplied by 3 raised to power 8 minus 1 over 3 raised to power 8. Do not forget that this is a multiple of 3, so it becomes 3 raised to power 3, which is 27, over 2. Don't forget that this is 1 over 2 raised to power 8, which can become 3 raised to power minus 8, in brackets 3 raised to power 8 minus 1. So when I apply the law of indices here, what does it become? 3 raised to power 3 minus 8 over 2, 3 raised to power 8 minus 1. So eventually, what do I have? 3 raised to power 5, 3 raised to power minus 5 instead, over 2, then 3 raised to power 8, then minus 1. So finally, you know that this guy can come down according to inverse law. You can check up on our lots of indices. Then it becomes 1 over 2 times 3 raised to power 5, then 3 raised to power 8 minus 1. And eventually it gives us 3 raised to power 8 minus 1 over You can leave it like this. There's no point. Or you can say 2 times 243, because 3 raised by 5 is 243. And that will give us 3 raised by 8 minus 1 all over 6, 8, and 4. That's our answer. So that is the sum to the 8th term of that progression, which is our answer. But the next question now is this applicable to sum to infinity? Can we solve for the sum to infinity of this progression? Can we? Yes, we can. Because our common ratio is 1/3 and is less than 1. So it is applicable, so we can. So if that is the case, I just need to bring this part of the board so that I can explain it better. So I can explain it better. How do I get the sum? So I have number 2, 9, 3, and 1 all the way down. My first term is 9. My common ratio is 1/3 as I've gotten. Then my sum to infinity is A, 9 over 1 minus 1/3, and that is 9 over 2/3 when you subtract. Then 9 times 3/2, and the answer is 27/2. That is sum to infinity. Don't forget, it was not applicable here because our common ratio was greater than 1. It's applicable here because our common ratio is less than 1. So that is all you need to know, basically. You need to know that you can easily navigate your way around other questions. The other problem you can solve based on this basic knowledge that you have already, it already informed you on what and how to get this job. Do you understand? So you can try number 3 and drop your answer in the comment section while we check it out. Thank you for being part of this class once again. Do well to subscribe and turn on your notification bell so that you can be informed when the video is posted. Thank you.